video that we're going to go over for lesson 4.6 about limits at infinity and asymptotes. Now, to help you with this, I would highly encourage you at this point to take out your Chromebook. If you're watching this on your phone, if you're watching this on your Chromebook, then you already have your Chromebook available. I'm going to be using Desmos in pretty much all of these to either do the problem or confirm the calculus or algebra that I'm doing. Okay, so the first part here, talking about limits at infinity, is going back to a little bit which we talked about in our unit 2 on limits. So basically our first calculus unit. And we're going to look at what happens as x approaches infinity or negative infinity of your function. And essentially, if you look at these as you move, all the way to the right or all the way to the left in the x direction, if you approach the same constant, that same number L, then what happens is you end up having a horizontal asymptote at that value y equals whatever that number is. All right, so you can see it graphically here as well. And we're going to do a few of these problems together to show you how you can use some limit laws and algebra to solve this, as well as using, obviously, Desmos, since that will be available to you when we take the test. Okay, so let's try this first one. It says to evaluate the limit as x approaches infinity of this function. So I have the limit as x approaches infinity of 5 minus 2 over x squared. Now I'm going to use some limit laws here to rewrite this. Again, this is really more work that we did a couple units ago. So the limit as x approaches infinity of 5 minus 2 times the limit as x approaches infinity of, and watch what I do here. I'm going to do actually do this, 2 times the limit as x approaches infinity of 1 over x times the limit as x approaches infinity of another 1 over x, right? Because 1 over x times 1 over x is 1 over x squared. All right, now let's talk a little bit about something we went through a couple units ago. The limit as x approaches any number, like in this problem, infinity, it doesn't matter if you just have a constant. So the limit as x approaches infinity of 5 is just 5 minus 2 times. Now, something that you would have talked about probably in middle school or early high school is when you do 1 over a really big number, you get a really small number. So the limit as x approaches infinity of 1 over x is going to be approaching essentially 0. And same thing for this one. So 0 times 0 times 2 is 0. So 5 minus 0 is 5. So that's the limit as x approaches infinity of this. So if I do the same thing, right, but this time look at as it approaches negative infinity of this. So the same work, just going to have x approaching negative infinity of 5 minus 2 times the limit as x approaches negative infinity of 1 over x times the limit as x approaches negative infinity of 1 over x. Very, very similar reasoning here. 1 over a really, really, I guess I should say the magnitude of this number would be big, right? 1 over negative a million is actually a very small number. But if you take the absolute value of negative 1 million, you get positive 1 million, which is a magnitude-wise very large number. So these are still going to be 0. So 5 minus 2 times 0, so which gives you also 5. So because from looking at the limit as x approaches infinity and the limit as x approaches negative infinity of this function were equal to the same value, that means we have a horizontal asymptote at this number. So horizontal asymptote at y equals 5. All right, now let me go to Desmos so I can show you, graphically what I'm talking about here. So we'll go to Desmos. I'll put this one in here. All right, so if you look at what's happening here, I'll move this over for just a second, right? You can see that as I move far to the right, we're approaching that y value of 5. Same thing all the way to the left, right? So we have an asymptote at y equals 5, okay? So that's the first one. I'm going to do the same thing, but for this one here, okay? Okay, so for this next one, the function is sine of x over x. And this one's a little tricky, right? Ultimately, I want to look at the limit as x approaches infinity or x approaches negative infinity of this. And the way you want to think of this first is to just look at the numerator by itself. So we have the sine of x. And when you graph this, when you guys were in pre-calculus last year, the sine of x function had your y values, the highest y values touched 1, and the lowest y values touched -1, right? That word amplitude is something you did when you did trigonometry. So essentially we're saying this is between 1 and -1, all right? Now, if I do the same idea, right, and say that this is sine of x over x, then I need to put these also over x. So really, if I look at the limit as x approaches infinity of -1 over x, or the limit as x approaches infinity of 1 over x, right, a positive one, this is very similar to what we did in the previous problem, with that x being in the denominator. 1 over, or even -1 over a really, really big number is going to be 0. So this kind of brings back something we talked about a couple units ago, but this idea is what we call the squeeze theorem. So if the limit of these two on the sides of the actual function we care about are the same, then the value that's in the middle must also have the same limit. So the limit as x approaches infinity or negative infinity of sine of x over x is going to be 0. So the limit as x approaches plus or minus infinity of sine of x over x equals 0. So what that means is that we have a horizontal asymptote at y equals 0. Now this is really interesting. I'm not sure if you read the kind of the intro to this section, but if you did, you would have already seen this. Most of you probably haven't had the time. I know you're super busy. So let me show you what's interesting about when I graph this one. So take this one off, put this one on. All right, so if I just take kind of a look here, again, y equals 0 is the asymptote. What you should notice, though, is that we are crossing, let me kind of zoom in, actually. We are crossing the asymptote infinite times. But what's cool is as you move all the way to the right, as you move all the way to the left, is that you're going to be getting closer and closer and closer to y equals 0. So this is one of those instances where we actually are crossing the asymptote, but as we move far to the left and to the right, we're going to get closer and closer each time we cross the asymptote. Okay, so that's it for the second one. Okay, so for this next one, what I want to do first is I want to first just look at, this is talking about the inverse tangent function. So first I want to look at the limit as x approaches infinity of the tangent function. Okay, so let me show you graphing what happens when you graph the tangent function if you forgot from your trig last year. Okay, and this is going to help us ultimately get to the problem. So I'm going to go ahead and put this one out here. Let me do a new line down here. So tangent of x, and I just want to focus on values. Let me change this to pi over 2. All right, I want to show you that if you look, right, if you look between negative pi over 2 and pi over 2, that the limit as x approaches infinity of tangent, right, is going to be moving towards that vertical asymptotes at pi over 2 and negative pi over 2. Okay, so when you look at, let me try to show you what I mean when I write it algebraically. All right, so let me actually do it like this. So instead of infinity, let me write pi over 2, and we said the limit as x approaches pi over 2 of the tangent of x is approaching infinity. All right, so what I can do now is if I'm doing the inverse, right, this problem is actually about the inverse tan function, this one here. So what I can do is I can actually switch places, right, kind of like when we switched x and y when we did this with in algebra. If we switch this, so my infinity goes there, this becomes the inverse of tangent, then this is going to be equal to pi over 2. All right, so that same idea, all right, if I do x approaches negative infinity of the inverse tan function, you're going to see that it approaches negative pi over 2. So let me show you in Desmos what I mean by that. Okay, so here's the graph of the inverse tangent function, right? And so if you look as we move to the right, right, we are approaching an asymptote. That horizontal asymptote is pi over 2. And if we move to the left, then this is also approaching pi over 2 as well. Okay, so let me switch back this step. Let's make that just 1. Delete it. And just write 1. Right? I don't know if it liked that. Oh, it didn't like that. Let me just write the number 1. That didn't work either. Okay, anyway, that's fine. I'll put in my keyboard to type in the number 1. There we go. Okay, so essentially what I'm saying is your horizontal asymptotes, there are 2 of them. One is y equals positive pi over 2, and one is y equals negative pi over 2. So we have 2 horizontal asymptotes, so 2 horizontal asymptotes. We have y equals pi over 2 and y equals negative pi over 2. Okay, now that's it for looking at finding limits as x approaches infinity or negative infinity. All right, again, that was all just to help us find horizontal asymptotes. The next thing I want to do is talk about end behavior. You guys have been talking about this for a couple of years now. We first started talking about this kind of in the, I think, quarter 3, maybe even quarter 2 of our Algebra 2 units. All right, we were looking at graphing polynomial functions using end behavior. This is when I would do that silly dance for, the degree is even or odd, the leading coefficient is positive or negative. This is just going to continue to kind of expand on that. All right, and with most of these problems, all these problems, I'm just going to be using Desmos to help me look at the end behavior. But as we talked about in the first couple, your function f of x approaches a horizontal asymptote y equals L if as your x is approaching positive or negative infinity. That could happen. The function could also approach infinity or negative infinity in the y value. All right. And then the function does not approach a finite limit, nor does it approach infinity or negative infinity. In this case, the function is said to have oscillatory behavior. Okay. So let's try one right here. Okay. So we want to look at the limit as x approaches infinity of negative 5x cubed and the limit as x approaches negative infinity of negative 5x cubed. Now, what I like to do with these is I'm going to do the graph of it, but I'm also going to be using a table. Sometimes it helps to do a table if it's tough to see with the graph. So if I look at this one here, right, you might be able to see it just by looking at it, all right? But as x approaches infinity and as x approaches negative infinity, you can see that looks like we have some interesting asymptotes going on. So I'm going to make a table here. Okay. So as x approaches negative infinity and x approaches positive infinity, you'll notice that our end behavior, right, as we move to the negative x values, we're approaching positive infinity in the y values, and kind of the opposite for as we move to the right, right? As we move to positive infinity, our y values are moving towards negative infinity. So what I'm saying here is that as we move to the right forever, right, you'll notice that we were approaching a y values of negative infinity. And as we move to the left forever, we're approaching y values of positive infinity. And you probably know why that happened, right? The main thing that happens is because our leading coefficient is that negative 5, all right, which causes it to have that reflection across the x-axis, the y-axis. So essentially what happens is that you, instead of looking at this with a leading coefficient of positive and an odd degree, we're essentially doing this the other way. So this, as I said, is just kind of a continuation or expansion of something we did in Algebra 2. Okay, let's look at the next one. All right, 2x to the 4th power. So I want to find the limit as x approaches infinity of 2x to the 4th power and the limit as x approaches negative infinity of 2x to the 4th power. Again, you could just do a sketch right now. You know the leading coefficient is positive. The degree is an even degree, right, of 4. So you know that their end behavior is going to be both going up, so the same direction because it's an even degree, and a positive leading coefficient means they both go up. So if I look at this one here, you'll notice both are going up forever. So as I move to the left or to the right, it doesn't matter. I'm approaching positive infinity in my y values. Okay, so that's it in terms of the end behavior of these power functions. Again, this is hopefully just feels like a review of a combination of things from algebra as well as some calculus from a few months ago. Let's do a few more. Okay, we've got a couple here that I want to determine the end behavior using the graphs. And then what I want to do at the very end here is I want to show you how to use all the stuff we talked about in the previous lesson and in this lesson to help us sketch one of these graphs. Okay. So let's go. I'm going to try to go a little quicker so you can kind of get through the end of this video in one period. So again, I'm just looking at the limits as x approaches infinity of this function and the limit as x approaches negative infinity of this function. All right, I've already got it ready for us in terms of the graph. So it's right here. Okay. All right, now you can see that this one's a little different than the ones we just did. It looks like as I move to the far right, I'm approaching an asymptote, and to the far left, that same asymptote, okay? So if you're having trouble seeing it, right, visualizing what the number is, all right, you can always use a table, and something that we talked about with our work in Algebra 2, you can see this is a rational function, and I told you that to find the horizontal asymptote, when the degrees are the same, in this case, both degrees are 1, it's the leading coefficient of the top over the leading coefficient of the bottom. So watch what happens when I approach negative infinity. I'll do a negative 1,000, positive 1,000. You should notice we're approaching 1.5 for both of those, which should not surprise you because the leading coefficient of 3 divided by the leading coefficient of 2 is 1.5. So because as I move to the right and to the left, I'm actually approaching the same number. Don't know what this is. Go away. Thank you. Because I'm approaching the same number of 1.5 or 3 halves, that means we have a horizontal asymptote at y equals 1.5. Okay, so again, a lot of algebra going on here with some limits of calculus. Okay, let's look at the next one. All right. This one says we have another rational function. You can see that the degree of the numerator is actually less than the degree of the denominator. Don't know if you remember what this meant in terms of the horizontal asymptote, right? But this means the horizontal asymptote is going to be 0, y equals 0. So you'll see when we graph this and I show you the table what is happening to this one. All right, so we go back to Desmos. Let's look at this one now. Interesting little blip there. Kind of cool. I've never seen that before. All right, but you can see as you move to the right and to the left, we are approaching a y value of 0. I can use a table if you'd like to see more of what's happening. So negative 100, let's do 1,000. Okay, I'll do 100 so it doesn't use scientific notation. Positive 100, you can see we're getting closer and closer to 0. So the idea here is that we have as our end behavior, as we move to the left and to the right, we're approaching that same y value of 0, which means we have a horizontal asymptote at y equals 0. All right, so another example involving rational functions. Let's try the next one. The next one, another rational function. This one, though, you'll notice the degree of the numerator is greater than the degree of the denominator by exactly 1. All right, and when we talked about this a couple years ago, and hopefully when you looked at this in your pre-calculus class, you would have noticed that this means there is no horizontal asymptote, all right? But there is something that we call in pre-cal, I called it a slant asymptote, or algebra 2, I called it a slant asymptote. And in the textbook here, they call it an oblique asymptote, all right? So both of them mean the same thing. So you'll see when I graph this that we don't have what we've been seeing recently. We don't have the horizontal asymptote. We have a slant asymptote. Let me do this. All right, so you can kind of see that slant asymptote there. If you wanted to find the slant asymptote, right, if you wanted to find it, then you would have to use either long division or synthetic division. All right, we'll make a table to help us with our end behavior here for a second. So negative 100, positive 100. You'll notice we're approaching, let me see what happens when I do 1,000. You'll notice that we're approaching positive and negative infinity. All right, and I'll do some algebra if you want to find the slant asymptote, and I'll graph it so you can see it a little easier. But to answer the question is, as we're approaching positive infinity in the x direction, we have approaching a positive infinity in the y direction. Same thing here. So let me do that real quick. Synthetic division. So we put -2 in the corner. We have 3 for x squared, 4 for x, 0 for the constant. Bring down the 3, multiply by the -2, you get -6. Add, you get -2. -2 plus or times the -2 is 4. All right, and so the slant asymptote, I used to always call it SA, is y equals 3x minus 2. All right, so watch what happens when I graph that. I think you'll see it on the Desmos a little easier. Again, this isn't really necessary in terms of answering the question, but just so you kind of see how this all connected to your work in pre-calculus. So there it is. You can see the blue line is our slant asymptote, and these curves are following it. All right, so that's it for that one. Let's move on to the next one. The next one is we have 3x minus 2, and in the denominator we have a radical. All right, so I'm going to look at that plot real quick. So I'm going to take this one away, and I have it right here. Okay, so you can kind of see what's going on. I'll do the table again and type in, what is like negative infinity. Yep, okay. And then type in positive infinity, or like 1,000. You can see we're approaching, as we move to the far left, we're approaching negative 1.5, and to the far right, we're approaching positive 1.5. So our end behavior here is we're approaching a constant. So that means we're going to have asymptotes. So the limit as x approaches infinity of 3x minus 2 over the square root of 4x squared plus 5 is equal to positive 1.5. And the limit as x approaches negative infinity of this same function, as we saw with the Desmos table, was negative 1.5. I'll show you again just so you can see it. All right. So we have 2 horizontal asymptotes in this one. So 2 horizontal asymptotes, y equals 1.5 and y equals negative 1.5. Okay, we're almost done in terms of using Desmos to describe the end behavior, and then we'll have one pretty long problem to kind of put all this together from previous lesson as well. Okay, so this one has a e's in the numerator and the denominator, so you guys should know hopefully at this point that e is just the base 2.718, but it's just an exponential function, the natural exponential function. So when you graph this one, right, when I graph this one, all right, you're going to see we have our asymptotes again. We do have a vertical asymptote. I'm not really worried about that right now, but as I move in the end behavior, I'm approaching, it looks like, the same horizontal asymptote. So let's do a table here, see if we can figure it out. So negative 100 is 0.2857. Positive 100 is negative 0.6. So we have 2 horizontal asymptotes. My apologies. And it looks like, based on what I see in the problem, I see 3 over negative 5. That's negative 0.6. So I'm assuming that 2/7 is 0.2857. Let me just confirm. 2/7. There you go. Yes. So that ends up being how they got those 2 fractions. So as we move to the left forever, so approaching negative infinity, let me keep it consistent. I've been using positive infinity first, so that's fine. So we'll do positive infinity of 2 plus 3e to the power of x over 7 minus 5e to the power of x. Right, so positive infinity is going to give us negative 0.6, which if you wanted to write negative 3/5, that's fine. And for this one, as we approach negative infinity of the same function, we approach the decimal 0.2857, which I just showed you is the same as the fraction 2/7. Okay, so that means we have 2 horizontal asymptotes. One is y equals negative 0.6, and one is y equals 0.2857. Okay, that was a lot of work with Desmos, trying to figure out the end behavior and ultimately leading to lots of asymptotes. Now the last part. All right, so the last part is I'm going to be doing a lot of stuff from algebra, all right, even some stuff from your days in pre-calculus. And then ultimately, I'm going to be using some stuff we talked about in the previous lesson and the one before that, talking about critical points. All right, so finding all of this information would be allow us to figure out how to sketch this if we didn't have a graphing calculator like Desmos. All right, so I'm going to find all this stuff and show you kind of how you would use it. But ultimately, because we do have Desmos, we can just graph it, and I can show you how everything we found matches up with our graph. Okay, so I'm going to do one of these because it is a long process. All right, I'm going to follow all of these steps. Okay, so the first one, kind of show you here. The first step says to determine the domain of the function. Well, this is a polynomial function. So for step one, the domain is going to be negative infinity to positive infinity. There are no values for x that are going to cause me any issues. All right, so step one is finished. Step two says to find the intercepts. All right, well, I know to find the y-intercept, I just plug in 0 for x. So I do f of 0. So 0 minus 1 squared times 0 plus 2. So we get negative 1 squared is 1. 1 times 2 is 2. So my y-intercept is 0, comma 2. For the x-intercept, this is whatever makes the function 0. So that would mean solving this. So setting equal to 0. And so my x-intercepts are going to be positive 1. Right? 1 minus 1 is 0. 0 squared is 0. And my other one is negative 2. So I have two x-intercepts. One at negative 2, 0, and one at 1, comma 0. All right, so that's the second step. The third step, all right, says to look at the end behavior. So as x approaches infinity, as x approaches negative infinity, do we have any asymptotes? So let's see. So the limit as x approaches infinity of x minus 1 squared times x plus 2. So you can plug in really big numbers if you want, right? I mean, I think even 100 is probably enough here. So you have 100 minus 1 is 99. 99 squared is a very big number. And then that's a positive, very large positive, times a very large positive gives us a very large positive, so infinity. Same thing if I were to plug in negative infinity right here. So if I plug in a very large negative number, and by large I mean like the absolute value of it would be big. So negative minus negative is still a negative. But when you do a negative squared, you get positive. But then when you plug in a negative to the negative plus 2, that's a negative. A positive times a negative will give us a negative. Okay, so that makes sense in terms of our end behavior, because if I were to multiply this all out, you'd see I have a cubic function. Let me do that real quick. So I have x squared minus 2x plus 1 times x plus 2. So that's x cubed plus 2x squared minus 2x squared minus 4x plus x and then plus 2. So that's x cubed. The x squared terms make 0. And then that makes minus 3x. And this is plus 2. So with the leading coefficient being positive and my degree being odd, my end behavior kind of matches with what I saw as I evaluated these limits. Okay, so that's step 3. Step 4, determine whether f has any vertical asymptotes. Vertical asymptotes, really when you're thinking about this, that would be whatever makes the denominator of a rational function undefined. This is not a rational function, right? They give it to us factor, but I just distributed it out and saw it's a cubic trinomial, so we're not going to have any vertical asymptotes. Okay, now step 5 and step 6 is stuff that we did in previous lessons, looking at finding critical points and determining where my function is increasing, decreasing to find any local extrema. And then step 6 is that second derivative test to look at where we have any concave up or concave down intervals. Again, you can refer back to that image that I showed you, that when it's concave up, you think it like a cup, so it can hold water. Concave down, think like a frown. All right, so it cannot hold water. Okay, let's try number 5. So let's find, I'm going to move to the next slide. Let's find the derivative. All right, so that's going to be d dx of, and I just distributed it out already, so x cubed minus 3x plus 2. So when you find the derivative of that, you get 3x squared minus 3. okay? And I want to find critical points, which means set this equal to 0 or find any values that make it undefined. I know that with a quadratic binomial, I'm not going to have any values that make it undefined, but I can figure out what makes it equal to 0. If I factor out a 3, I'm left with x squared minus 1 equals 0, and boom, that's dots. So I have x minus 1 times x plus 1 equals 0, so my two critical points are plus or minus 1. Okay, so what I'm going to do to determine the intervals at which my function is increasing and decreasing and ultimately to if I have any local extrema, I'm going to split up my domain, which I did in part 1. Remember that one? Excuse me. My domain was all real numbers, so I'm going to split that up into a table like we did the previous lesson, where I'm going to have negative infinity to negative 1, negative 1 to positive 1, and 1 to infinity. Okay, then I'm going to do a test point. Right, so this would be my interval, then my test point. So I'm going to use negative 2, 0, positive 2. This would be where I look at my sine of my f prime of x. Okay, one second, let me check something real quick. Okay, so when I plug this in, you can plug it into the original derivative before I factored. Right, you can plug it into this, you can plug it into this, right? And I'll even write down that 3 in front. You could plug it into that one too. Doesn't matter. But the key thing is when you plug it in, you want to know what the sign is. So the way I do this is if I plug in negative 2 to x squared, that gives me a positive, right? And that's a positive 4 times 3 is 12. 12 minus 3 is a positive 9. Okay, so that tells me the function is increasing. So this is my conclusion. If I plug in 0, I'm going to get a negative. So the function is decreasing on this interval. And then if I plug in positive 2, I get another positive. So the function is increasing. All right. So not only does this tell me where the function is increasing, but it also tells me that because I'm going from increasing to decreasing, I have a local maximum at my first critical point, which is at x equals negative 1. And since I'm going from decreasing to increasing, I have a local minimum at my other critical point, which is x equals positive 1. So again, that's straight from a previous lesson, 4.5. Okay. Now, the last part. One more slide here before I graph it. I'm going to do the second derivative test. So I need to find the second derivative, which is d dx of 3x squared minus 3, which is going to be 6x. Again, I'm trying to figure out what makes this undefined or equal to 0. Nothing's going to make a linear function undefined, so just set it equal to 0 and you get x equals 0. So if I divide up my domain, my domain of negative infinity to infinity into two intervals of negative infinity to 0 and then 0 to infinity, I can figure out if on these intervals, if my function is going to be concave up or concave down. So this is going to be test point. So I'll use negative 1 and positive 1. And then we have our sine of f double prime. Right, so this is that second derivative test. And then this is our conclusion. Okay, so plugging in negative 1 into 6 times that number, my sign is negative. So this is concave down from negative infinity to 0. If I plug in 1 times 6 is a positive 6. So this is concave up. So again, concave down means it'll look like a frown. Concave up means it'll look like a cup able to hold water. Okay? Now, it also means that when we switch from concave down to concave up at x equals 0, we do have something called an inflection point at 0, comma, and we actually found this at the very beginning of the problem, finding the y-intercept is 0, comma 2. Just so happened to have an inflection point at the y-intercept. So now I'm ready to sketch it, all right, or make the graph. I'm going to go over to Desmos now. So this is my graph, and I'm going to walk you through kind of everything we just found. All right, so here we go. Here's what it looks like on the graph. Let's take these off. Here it is. All right, zoom in for my things. All right, so we said let's kind of walk through it. So the domain is all real numbers. The next thing we found were the intercepts. We have two intercepts. We have two x-intercepts, I should say, at 1, 0, negative 2, 0. Confirm. Let's have that. Where is it? Right there. We have two x-intercepts. We have our y-intercept at 0, 1. Oh, sorry, excuse me, 0, 2 right there. Okay. The next thing we found was we looked at our end behavior. So as x approaches positive infinity, as we move to the right, our y values are approaching positive infinity. As our x values are moving to the left, our y values are approaching negative infinity. That makes sense. We've done that many times before. Go away. I don't care. Okay. And then we found our extrema and increasing and decreasing. So if you look, we have a relative maximum, we said at negative 1. There it is, negative 1, 4. We have a relative minimum at this critical point, 1, 0, which happened to also be an x-intercept. And you can see our function is increasing until that first extrema, then decreasing, and then back to increasing. All right. Now the last part was looking at the concavity. All right. So because if you look at the beginning, I know we're increasing. This can be a little confusing, but we're increasing and our concavity is actually down, right? See, it looks like a frown. So this right here is a frown until we get to our inflection point, which is the y-intercept. Now after the y-intercept, we now think it looks like a cup. So our concavity is concave up. All right, so we are concave up from 0 to infinity. So kind of just bringing it all together in terms of this sketch. All right, so if you wanted to draw the sketch here, you could, but ultimately, I just want to show you what's kind of happening here. Something like that. Okay, so hopefully you're not too worried about this section because so much of this is done with Desmos, and you will be able to use Desmos on the test for this chapter. All right, good luck.